Hello, everybody. Welcome to my talk, Press F to Move It, a quest to discover how a web shell appeared. So our quick agenda for this presentation is we're going to go over what this Progress MOVEit Transfer application is, talk a little bit about who the threat actor got attributed to, and then deep dive into some technical discussions about how Mandiant ended up investigating this particular incidents and exploitation of this application. So a little bit about me. I'm Peter Ukhanov. I'm a senior Mandiant consultant with the Google Public Sector group in Google, and we focus on various state, local, and governmental agencies, as well as companies that are associated with government. Prior to joining Mandiant last year, I worked at Dragos for a little bit, doing industrial incident response. And then I started my career out with the Defense Information Systems Agency, a DoD sub-entity performing incident response for various DoD organizations. And then outside of work, I picked up mountain biking after I moved to Charlotte a couple of years ago. And then I enjoy, as all nerds enjoy, video games and cooking. So what is Progress MOVEit Transfer? So this is a piece of software that was formerly known as Ipswitch MOVEit DMZ, and you would see references to Ipswitch and DMZ in various files, logs that this application would generate. So it is a managed file transfer solution, similar to like Dropbox, Google Drive, OneNote, but for a enterprise environment. That way you can set it up on-prem and you have full control over what happens, how it happens in that application. These managed file transfer solutions, they tout secure collaboration and automated file transfer. And as we can see, as we start investigating, how it got exploited, some of these secure collaboration features are actually their possible downfall. One unique capability of MFTs and MOVEit in particular is that they support multiple instances of an environment per deployment. So that means you can set up unique enclaves per installation that have dedicated controls to access those enclaves. And in case of MOVEit, there were multiple ways you could interact with the application. Some of the more legacy methods, so FTP, I served up an FTP file server that you could automate tasks to pull files, upload files. There was a web UI that majority users would probably use, and it also had guest access, which we will see that guest access was leveraged as part of the exploit chain. And then finally, there was a web API for web API stuff. So you can develop apps to integrate with that stuff. And this web API would also end up being used by the attacker to successfully exploit the application. Now, from an attribution perspective, so when Mandiant started investigating all these incidents regarding this application, Mandiant originally attributed this activity to an UNC 4857. And what we call an UNC is a uncategorized cluster of threat actor activity. That way, meaning we've never seen this potentially before. So as more and more information came in from the various investigations, public reporting, based on some of the targeting, infrastructure overlap, and then finally when CLOP said, hey, this was us, this UNC got merged into a FIN11 threat group that Mandiant has tracked. And they're a financially motivated threat group that's been active since at least 2016. Historically, FIN11 has conducted some of the largest and longest running malware distribution campaigns observed amongst Mandiant tracked FIN groups today. And they've recently started to monetize their operations using data exfil. As we saw in this case, the threat group ended up using a zero-day vulnerability in servers that allowed them to exfil a lot of data. And this wasn't the first time that this threat group has used a server vulnerability. Some of their previous known public attacks included attacking the Exalion legacy file transfer system, secure SolarWinds secured FTP servers, and then the For2Go Anywhere managed file transfer solution relatively recently as well. Now, from a timeline perspective, this timeline looks pretty basic. The earliest that public reporting suggested that Fin11 started to be interested in MOVEit goes back all the way to 2021, so almost over 2 years at this point, with some public reporting indicating that somebody was scanning MOVEit instances to see what were they out there. Now, as we started investigating the various compromises, we were able to determine that back in April of 2022, there was large volumes of attacker scanning against various MOVEit instances, and this was observed by the various Mandiant investigations. Fast forward to a little bit over a year, to approximately May 15, 16 of 2023, and again, we saw mass scanning of MOVEit instances over those 2 days, with some instances getting scanned anywhere from like 2 to 3 times. And then on May 27th, 2023, D-Day, that's when the max exploitation and data theft of the various public MOVEit instances started to occur. Keen eye among you will recognize this weekend as potentially Memorial Day weekend in the US, and on May 29th, which was actually Memorial Day in the US, we started to see additional scanning activity against instances that weren't successfully exploited in that original wave of attacks. Moving a couple more days later, on May 31st, the CVE got finally publicly announced by the vendor, Progress in this instance, announcing that there was a SQL injection vulnerability and that it was under active exploitation. And their recommendation was to take down, your MOVEit instances from public access and to perform incident response and investigate what kind of data might have been breached. And then a week later, almost June 6th, that's when Fin11 CLOP publicly announced that this was them performing exploitation and performing proactive red teaming to secure your infrastructure. And then ever since then, CLOP has been doing negotiations with affected entities, and then if somebody potentially didn't pay up or negotiations broke down, they would release that information on their leak site. Now, how did we end up performing this investigation, figuring out what got affected, impacted? We ended up using a variety of data logs, focusing mainly on the MOVEit application logs, as well as other host and application system logs. In the case of MOVEit, there was 3 main logs that were most beneficial from an analysis perspective. There was this DMZ_web log, and that ended up capturing a lot of requests, errors, including full SQL injection queries, stack traces from exploits, execution, failed exploit execution. Fun fact about this log, depending on how you had your MOVEit instances configured, if you're using SQL Server as your backend or MySQL, certain commands that the attacker was doing would fail or show up slightly differently, and those would cause a log to be created. Additionally, there was this DMZ IS API log, and that one particularly captured, in certain instances, full request response. So you could see the full headers and request bodies that were being sent to the application, and that allowed us to see what kind of metadata they were submitting to the application to cause the vulnerability. And then finally, there was a MOVEit audit log in the application, and this log logs all audit events in MOVEit. So this includes file downloads, login events, logouts, file uploads, and by default, it gets logged to the database that backs the MOVEit application. And what we saw with this attacker, they were actually coming in after they finished their exploit chain and deleting the audit logs from the database. So they were trying to make it harder for anybody to do investigations. One thing that we saw in certain instances, depending on the organization, there was an option to actually forward the MOVEit audit logs to Windows event logs or syslog, and that would just make it a lot harder for an attacker to clean up that log. Plus, you could do additional detections, right, as that data fed into your SIM, for example. Now, from a OS/database perspective, Microsoft IIS logs ended up being invaluable for this investigation. Those logs standard web requests, including by default how much data was being transferred, as well as duration of this request. So that made figuring out, was there a download a little bit easier. Additionally, one thing that we did find out and became very helpful, as you'll see in the next couple slides, are the SQL transaction logs. And SQL transaction logs are logs kept by the database anytime a query modifies data in the underlying database. So any insert, update, delete statements that get executed get saved to this file so that you can replay it in case something happened, right, with the database. And then finally, and this, I wouldn't say super useful in some of these investigations, but if you had network security tools, so like NetFlow, Zeek, for example, they ended up being pretty helpful to seeing, the volume of traffic being sent across the environment, as well as any EDR tools, endpoint detection and response. That way you could have potentially seen that web shell actually getting dropped on the system and use those logs to investigate if there was any other possibilities for like lateral movement or any other adversarial actions if it was some sort of different threat group that was attacking you. Now, the exploit chain. The exploit chain ended up being, from all the logs that we've seen, about 16 requests to multiple endpoints in the application that resulted in this human2.aspx page getting dropped on the server and then used by the attacker. The chain, some of the pages that were used as part of this exploit chain was this guest access.aspx that was leveraged to generate valid ASP.NET session IDs that then the attacker took, put them into this SQL injection that existed in this MOVEit ASAPI.dll endpoint. And using the SQL injection, they were able to do privilege escalation, stage their payload for deserialization, as we'll see in a couple slides, and then perform that artifact cleanup, including audit tampering. And then the key API that was responsible, and that API endpoint, was this API v1 that MOVEit exposed for programmatic access to the application. And this API was leveraged in combination with that SQL injection to actually perform the deserialization vulnerability to deploy the lemur loot web shell, as we called it. And this API was used to create resumable file upload that contained the payload, and then use the SQL injection to stage it for exploitation. One thing to note, we did note that if the web API was disabled or not licensed, the whole exploit chain would fail and the attacker would come in and scan it again. Now, I talked about this web shell. What is it? Mandiant ended up calling it lemur loot. It's a C# web shell that was specifically developed to target the MOVEit Transfer application. It ended up getting a hard-coded password set for every exploit attempt, so that only the attacker could access it. And it performed multiple functions, everything from performing full-scale data reconnaissance and configuration enumeration, so getting stuff like your Azure Blob configuration settings, getting a full listing of files, folders, and users in all instances of an installation, and then performing some of these impersonation and admin creation capabilities. One interesting thing about this file is why it was called human2.aspx is so that it blended into existing pages that existed. There were various pages called human.aspx, machine.aspx, and there was a machine2.aspx, which is a legitimate page. So this way, if a regular admin looked at it, they would have had no idea that that page potentially was bad. Now, how did we figure out how lemur loot appeared? first things first, review all the various logs. A bunch of logs, scroll through. Somebody's going to be like, hey, I get tired of looking at logs. We did identify a web request in the IIS logs that ended up returning a status code 500. This particular request was that specific resumable file upload that ended up returning a 500, meaning something happened on the server. And using that timestamp, we ended up pivoting to the DMZ weblog, and in there you could actually see a full stack trace that got dumped to the log saying, hey, something happened with this binary formatter deserializer in this specific function of the MOVEit application. So next steps were pretty much just go decompile the application, take a look at where this specific function exists, and this is how that specific function looked. In this red box, I have highlighted this particular binary formatter that was exploited. And you can see here, this binary formatter deserializes whatever's in this upload state variable. So poking around the application some more, we find this function that sets this upload state variable. And here we can see that this this function is backed by this file upload info table. And both this comment field and state field in the database are encrypted, but only the state field is base64 encoded. And this will be quite handy in figuring out the actual payload. A little bit more about this file upload info table. Pretty simple, has a file identifier, comment field, potentially saying, hey, this file is being uploaded for XYZ reasons. And then some transfers IDs that are used internally, and the core field, the state field. That state field just tracks the file upload progress with some metadata. Now, knowing this database, we ended up looking at the SQL transaction logs, and what we saw in SQL transaction logs was the attacker using the resumable file upload API containing the base64 payload. In the comment, you could actually see the full insert statement. And here I just redacted a lot of the information because the strings ended up being super long. The attacker then used the SQL injection to copy the value from the comment field into the state field. Here's another screenshot of how it looked in this transaction log with a regular update statement where the encrypted payload value just got copy pasted into the right field. And then at this point, the attacker then used the resumable file upload vulnerability to trigger that deserialization vulnerability. And then finally, how does actually their cleanup look? The attacker then used the SQL injection to actually go in and delete that file that was being tracked as a resumable file. And that is just a regular delete SQL statement. So at this point, we had the encrypted payload from the database. How do we decrypt it and figure out what the actual raw payload was that was ran? Well, at this point, you should channel your inner attacker and we ended up creating our own, what I would call web shell to decrypt the payload. This is a screenshot, pretty straightforward, uses built-in functionality of the MOVEit Transfer application to perform decryption. One unique feature about MOVEit, as I've talked previously about these different instances in the application, you have to specify a correct instance ID to get the correct decryption key. One unique thing, the -1 instance ID is the installation 1 encryption key that is for the entire installation that is used by the system processes. There are other instances IDs. We originally were trying to use those, and the code would just error out saying, incorrect decryption key. When we ended up running this page, we got a base64 encoded payload back that we saw, the attacker inject. And then the only reason it returned base64 at this point is that so it was easier for us to transfer it back to our environment for analysis. And probably what everybody waiting for, what does the payload look? At this point, we got it, quest accomplished. We figured out how the web shell appeared on disk. So this serialized payload, this is a beautified version of it, pretty much did 3 things. It decoded a string in a specific header. then generated a GUID for a password, and replaced a predefined template variable, in this case, change me 1337, with that specific GUID password. And then the content of that string ended up getting written to disk. And if it was successfully getting written to disk, it would respond with OK, and then the specific password for this exploitation. This just explains why every single instance of a recovered lemur loot web shell had a different password. Now, from a post-exploitation perspective, after the attacker got the web shell on system, they performed data exfiltration using two primary methods. First one, using native functionality. They used lemur loot to impersonate an existing admin, logged in with that impersonated admin session, and then just clicked download all files from the page. And the web application zipped everything up and provided them a single download file. Now, in some instances, and this was reported in some public reporting about this in these investigations, the lemur loot web shell was actually used to download individual files. From a timing perspective, data exfil actually occurred anywhere from a few minutes after that web shell got dropped on the system to, we saw in some instances, several hours passed before data exfil occurred. So that's how the web shell got dropped and used. Now, how could a view potentially have prevented or detected this exploitation? From a detections perspective, as everybody, a lot of people recommend, monitor your web routes for new file creations. Typically you shouldn't have new files getting created, especially ASPX pages or code pages getting created in your web routes. You should definitely leverage some sort of EDR, especially on your key assets and specifically on your publicly facing assets. In some investigations, we saw some EDRs create an event that, hey, a potential web shell is getting created, but it never bubbled it up to an alert. And then finally, as I mentioned in the log section, forward all your logs to some sort of SIM, so you can do some additional enrichments and analytics. That way you can have more insight into what an application is doing. And here I have a couple of what potential things you could develop rules for. From a recommendations perspective, a lot of these managed file transfer solutions have retention policies built into them. So leverage them to automatically delete files so that if you do get exploited, you're not releasing 30 days worth of data or like terabytes of data potentially. Disable unneeded features in hosted applications would have saved some organizations in this instance. And then probably the big one, do not use this binary formatter that is available in .NET. Microsoft even says in their documentation, like, this function is unsecured. There's no way to secure it. So if you have that in your code, there's probably a chance that an attacker will find it and potentially try to exploit it. So that couple of recommendations, detections, hopefully that will, you can take that with you back to your teams and potentially develop something for your tools. From additional resource perspective, Mandiant ended up publishing a blog post going over this specific intrusion and exploitation, as well as a containment and hardening guides focusing on MOVEit Transfer, so that if you do have MOVEit Transfer, you can potentially apply this to harden your environment. And then, of course, Progress put out a technical article detailing all their findings, as well as linking to some other entities. Here are a couple of links to both the Mandiant blog post and the Progress report, as well as some other incident response firms that did analysis, including Huntress, which they actually created a video of the exploit, getting additional, getting shell on a system, and then Kroll investigated a little bit more of the data exfil portion. So with that, definitely a big thanks to all the various Mandiant consultants and analysts who tirelessly helped all the various customers that got impacted by this. Big thanks to the advanced practices, remediation, and Flare teams who supported all the consultants that were working with all the teams. And with that, that wraps up my talk. Thank you, everybody.